right, let's go ahead and do a sound check and make sure everything is working just fine. I can hear myself. Can I see my hand over my document camera footage? All right, and that's coming in too. Then I think we are good to go. Let me put away the headphones. And let's get started. So, let's see, what's our plan for today? Last time we covered, well, before any of that, sorry about yesterday. For those who were waiting for the usual Sunday stream, I had to postpone it, but only by a day, so hopefully it wasn't that terrible. I know it being on a weekday might not be so convenient, although I guess it depends on what part of the planet you're in. It might already be a weekday for some people. I know I have people watching from other countries, so I mean, at the end of the day, you still have the recordings, so there's that. But yeah, I was a bit worried that I would actually have to postpone it until Thursday, but I'm glad I took a Hail Mary chance and things worked out for today, so sorry about the delay for the 2 or 3 of you who actually wanted to see it on the usual schedule. Other than that, any other announcements and things to say? Oh, right. I forgot at the end last time to mention that there wasn't going to be a traditional office hours stream, and I'm going to say up front today that there won't be one today either because I actually still have a lot of stuff to do after this. In fact, I might end up cutting this stream short compared to other streams. Usually I go for about 3 hours. I might stop at 2 or 2.5. We'll see how we progress. If I feel like we reach a good stopping point for 2 or 2.5 hours, I might be stopping around there. And I think that's it for announcements. So, plans for today. Last time we finished talking about systems of objects, and we took a look at some of the interesting patterns that emerge when you're looking at objects, specifically objects that all move with the same acceleration. We found that a lot of what I called internal forces disappear, and you can get away with treating the system of objects like a single object that has just the total combined mass of all of the different parts, with the internal forces all disappearing. And I mentioned that that was just kind of a shortcut thing that you'll start to understand more and more with practice as you do things the slow way. And I recommended you just focus on doing things, step by step and not trying to take that shortcut. Make sure you understand your shortcuts before you use them. Speaking of which, I literally got texted this past week by one of my students who was reviewing something. She learned in AP Physics 1 that there was a certain shortcut that she could use for energy and springs. I know we haven't talked about energy yet, but my point still stands. And I had to remind her that there was a condition that she was missing, and that's why she was getting the wrong answer on the question that she was asking about. So when you use shortcuts, you need to understand them. You need to know why they work and when they do and don't work. You need to know their conditions. Anyway, I lost my train of thought. What was I saying? So yeah, we talked about systems of objects last time, and we got to play around with the concept of friction a little bit more, as well as tension. And for today, well, I wrapped up last time by just kind of introducing the basic idea of working with inclined planes, or just inclines or ramps if that's what you want to call them. And today we're just going to work with that. We already did all the derivation. We basically went over how you can switch from this XY coordinate system to this parallel perpendicular coordinate system. Parallel and perpendicular meaning parallel to the ramp or perpendicular to the ramp or incline or whatever you want to call it. Some people will still call these X and Y instead, which is, I guess, fine, but I would rather call them parallel and perpendicular because we're going to have problems where you are going to have forces that are using the traditional X and Y coordinate systems at the same time that you're dealing with a ramp. And I just feel like it's important to distinguish this from this. So that's, I mean, at the end of the day, it's personal preference, but I feel like it just makes communication easier. It's much clearer what I mean by X and Y if I stick to just it being what we've always used it for and give these a different name. So that is the recap. Let me see, was there anything else on our course plan? And of course, if you're new here, the link to this course plan should be in the description. It's just on my website, althetutor.com/physics1 course plan. And yes, Physics C is also going to be using this course plan because I haven't made a separate one for Physics C yet. I don't even know if I'm going to, but I'll think about it. It's mostly going to be a copy-paste, except a few modifications for topics that are not in Physics C. Let me see. So, yeah, and I highlighted, basically, our goal is to get through these 4 topics for today, and then that won't be the end of the force chapter. If you think this is the end, you missed the first stream on the topic of force, where I said I consider force to be the most important chapter in all of physics, and you're going to learn over the next few weeks that I meant it. We are nowhere near done with force, not as far as I'm concerned. We're going to be doing a lot of tougher problems in the coming weeks. But before we get to those, let's make sure that we know how to do the basic problems. So I did recommend that you guys try these for homework, and the solutions were available in the form of a video. My idea with each of these was to solve for a different unknown each time. So let me see. For this first one, the unknown was the mass. For the second one, the unknown was the force applied. For the third one, the unknown was the angle. And for the fourth one, the unknown was the acceleration. So if you were able to do all those, congratulations. Now you can do basically anything that is asked of you for a basic inclined plane problem. And then I also had this challenge problem, and I don't actually solve these in my solution videos, I don't think. So maybe we should start with this one. I'll go back to this in a minute. And then if you tried the one with friction, it's basically the same thing, except you have to add a friction force to your diagram. And if you got lost, the solution video is there, and there is this challenge problem. So yeah, I think that's what I'm going to start us off with for today. Let's go ahead and start with this one. So it says, challenge, solve the problem shown below, which is taken from my book, one of my books. It says, the coefficient of static friction between the 3 kilogram crate and the 35-degree incline of the figure is 0.3. What minimum force, F, I'm just going to call it force applied in my diagram, must be applied to the crate perpendicular to the incline to prevent the crate from sliding down the incline? What minimum force must be applied to the crate perpendicular to the incline to prevent the crate from sliding down the incline? Okay, let's switch over to our document camera and figure out how we want to do this. Is that all showing up on screen just fine? Yeah, all right, it's looking good. So I'm going to go ahead and draw a copy of the incline, and then here's going to be our object, and then the angle of the incline was 35 degrees, and they said it was a 3-kilogram crate. And it's a rough beam. And the coefficient of static friction maximum is equal to 0.300 if you want to be technical about it, but we're not doing sig figs here, so I'm not going to worry about that. You can worry about that in your AP chemistry class. All right, force diagrams. So we learned last time that the force of gravity, if you use this parallel and perpendicular as your coordinate system, then your force of gravity can be broken down into a parallel component and a perpendicular component. So that's what I'm going to do. On the AP exam, if they ask you to draw a force diagram, you would actually just excuse me, you would actually start with just the raw forces. Don't break any of them into components, but a lot of times in the interest of time, I'm just going to draw the components for inclined plane problems. So that's exactly what I'm going to do here. So there's going to be this component, force of gravity, sine of theta. I'm going to have over here force of gravity cosine theta, not drawn to scale. They may or may not be bigger or smaller than what I'm showing here. There was an unknown applied force. There's an unknown force applied. And there is a normal force, of course, because this thing is touching the incline. And the goal is to prevent it from sliding. So there's going to be a force of static friction. Force of friction static. Okay, so whatever our force of friction static is, if we want this thing to not move, then obviously it would also have to have no acceleration in the parallel direction of our incline. I'm going to use for my perpendicular direction, it's just going to be the normal perpendicular and away from the incline. And for my parallel direction, I'm going to say that positive is down the incline this time. So I'm going to say the parallel direction is down the incline this time. So that would mean if I do net force in the parallel direction, net force in the parallel direction, that has to equal the mass times the acceleration, which is going to be 0 in the parallel direction, is equal to, and I didn't plan this really well. It's supposed to be, I didn't make enough room for this. Okay, let me start a new line. So net force parallel equals mass times acceleration in the parallel direction, which we want it to be 0, equals positive forces in the parallel direction. That's going to be my force of gravity sine theta, minus force of friction static. And of course the conclusion we get from this, since 0 is equal to this difference, then force of gravity sine theta must equal force of friction static. Okay, and we know that the maximum static friction is greater than or equal to the actual static friction, which is greater than or equal to 0. So whatever our force of static friction is, force of gravity sine theta is less than or equal to mu static maximum times whatever the normal force is. We will hold on to this and come back to it later. So that takes care of everything in the parallel direction. Okay, what about in the perpendicular direction? Well, common sense would suggest that there's not going to be an acceleration along this axis, right? No reason for this box to accelerate along that line. So net force perpendicular must also be 0. Net force perpendicular must also be 0. Mass times acceleration in the perpendicular direction, and that's going to be 0. That is a very badly written 0, but at least you know from my voice what it's supposed to say. Anyway, I'm going to use up and perpendicular as my positive direction, down and perpendicular as my negative. So it looks like normal force is the only thing in my positive direction, and then minus force applied and minus force of gravity cosine theta. Okay, and I can add these two over to the left-hand side and get normal force is equal to force applied. I guess I flipped my left and right hand sides here, but that shouldn't be too confusing. I would hope we've developed our math skills enough at this point in the school year that we're not fazed by this. Okay, so that's our normal force. Now that we have this, we can substitute it into this expression. And if I go ahead and do that, then my force of gravity sine theta has to be less than or equal to mu static maximum times the normal force is going to be, in parentheses, the force applied plus force of gravity cosine theta. Okay, and my options now are to either distribute the static friction coefficient, or better yet, just divide it over so that I don't have to distribute. And I'm just going to divide it over. So I get force of gravity sine theta over mu static maximum less than or equal to force applied plus force of gravity cosine theta. Let's see, how about we go towards the top of the page now. I'll use this space over here. I can subtract force of gravity cosine theta, and I get force of gravity sine theta over mu static maximum minus force of gravity cosine theta is less than or equal to the force applied. Okay, and now I'm going to go ahead and plug in numbers. Yes, I could have substituted my numbers at any point, but as I mentioned in, I think actually the previous video and videos before that, when you do it this way, when you wait to plug in your numbers, it helps you just practice your algebra skills and sets you up for success with those expression problems that they like to ask on the AP exam. And also helps you discover things that you might be able to eliminate, information that you thought you needed that you actually didn't need. So anyway, substituting the numbers, force of gravity is just mg, so it's going to be 3 kilograms times 9.8. So 3 times 9.8 over the friction coefficient was 0.3. 3 times 9.8 times sine of 35. Sine 35. Okay, minus the same thing, 3 times 9.8 times cosine of 35. I want to go ahead and evaluate that. So calculator, squishing everything into here was probably not the wisest of choices. 3 times 9.8 times sine of 35, and is my calculator in degree mode? Yes, it is. Divide by 0.3, and that gives me 56.21, and then minus 3 times 9.8 times cosine of 35, and that gives me 32.127. I'll round it to 32.13. So all of this is 32.13 newtons. So 32.13 newtons is less than or equal to the force applied. So the force that you need to apply on this box to prevent it from sliding has to be at least 32.13. The question was what minimum force is needed to prevent the box from sliding, and that's exactly what we got. Normally, you'd be taught to just do this using equal signs and not even bothering with the inequality, but again, I think that it's insightful to still use this inequality relationship at least a few times before we start skipping on it, just so that we can make sure that we don't forget our understanding of the static friction force. Static friction force has some sort of maximum value, but doesn't necessarily attain that value unless it actually needs to. Something that a lot of students don't end up learning because either the teachers neglect it or the students forget about it, or both. But there we go, that takes care of that first problem. Next up. Oh, actually, before that, there's something I forgot from last time. It just came to me when I was talking earlier about the, where was it? It was the problem with, yeah, this one, the problem with the truck. I completely forgot to answer the rest of part B, which data is unnecessary. So the mass of the load was unnecessary data because it canceled out, but that's not the only unnecessary data. The mass of the truck was never needed for this problem, and also we didn't need to know anything about the friction or lack thereof between the tires of the truck and the road. And yeah, we also didn't need to know the normal force between the truck and the road. We didn't need to know anything about the truck or the forces acting on it. So that takes care of the parts I forgot from the truck problem from last time. Okay, now we can move on to our next problem. I'll go ahead and flip this sheet to its opposite side, and let's pull up that problem and read it and see what's in it. So it says, a force is applied on a 15 kilogram object in a direction that is upward along a rough incline as shown in the diagram. The object doesn't move. What is the coefficient of static friction? Oh, okay. I mean, I guess that's easier than the one we just did. But we can work with it. We can work with it. Actually, I think this is the one where we can derive a special relationship that comes up frequently, if I'm not mistaken. Oh, no. That's the one. That relationship I'm talking about is only for when the object is sitting still on its own. The applied force kind of throws a wrench in things. Let's have a look. So, incline is at 16 degrees. I know I'm not drawing it small enough to be 16 degrees, but I need room to draw stuff. So we're going to work with this exaggerated drawing of a 16-degree angle. And our object is 15 kilograms. The force that's applied on it is 57 newtons. The force that's applied on it is 57 newtons. Force applied equals 57 newtons. Is that even enough to push it up in the absence of friction? That's part of what makes this a trick question. I'm pretty sure this thing, in the absence of friction, would actually move down because, well, with the 16 degrees being so small, maybe not. We'll see. We'll do the math and we'll figure out which of the two cases it is. We need to do that math anyway to determine where we want to draw our static friction. So we've got our force applied. Of course, we're going to have some sort of normal force perpendicular to the surface and away from it. Force of gravity. I would normally draw it straight down, but in the interest of saving time, I'm going to go ahead and draw its components. Force of gravity sine theta down the incline, and force of gravity cosine theta perpendicular to the incline. And then, oh my goodness. And then we have the static friction that we need to decide whether it will be up the incline or down the incline. So let's figure out what force of gravity sine theta is going to be. Force of gravity sine theta equals mg sine theta. Force of gravity is 15 times 9.8, and then that times sine of 16 degrees. According to our calculator, that's going to be 15 times 9.8 times sine of 16 is 40.52 is equal to 40.52 newtons. Okay, that is less than 57, so in the absence of friction, this object would have moved up the incline. So the static friction, in order to prevent motion, must act down the incline. So the force of static friction, I'll draw it in orange, must be this. Force, friction, static. Okay, were we told anything about No, we need to find the coefficient of static friction. We were not told what it is. Okay. But now we have all the pieces. Now our diagram is complete. The rest is just equations. So let's do, how about green? Actually, I don't know if green is going to show up that distinctly under this lighting. I looked at the footage from last time and a bunch of the colors looked the same. I might just need to get some new light or figure out something for this lighting situation, because it wasn't like this before, but that's winter. We don't get as much sunlight, so I have to work with unnatural lighting. Where was I? So I'm going to do net force. Let's do net force perpendicular first, and then parallel. Parallel is where all the action happens with inclined plane problems most of the time. So net force perpendicular is going to be mass times acceleration in the perpendicular direction. What's the acceleration going to be along that direction? Nothing. We don't expect the box to move in any sort of way along this direction, so there shouldn't be any acceleration either. It's not moving along that direction, and it shouldn't start moving along that axis either, so that acceleration better be zero. So that's going to be normal force minus force of gravity cosine theta. And if you add force of gravity cosine theta to both sides, then you get normal force equals force of gravity cosine theta. And that's it for the perpendicular direction. Parallel to the incline, parallel to the incline, we've got mass times, well, we want the box to not slide, so our acceleration parallel to the incline, the problem requires it to be zero. And then I guess I'll do up the incline as the positive direction this time. I'll use up the incline as my positive direction, so that's going to be parallel, that's going to be perpendicular. Yeah, this time I'm going to do up the incline as positive, so that's going to be force applied minus force of gravity sine theta. And also, force of friction static would be down the incline, so also minus force of friction static. Static friction is going to be in our negative direction this time. Okay, and this leads us to what? I guess what we need to solve for here is the force of static friction, because that will help us find the coefficient of friction. So if I add force of static friction to both sides, I get force of friction static is equal to force applied minus minus force of gravity sine of theta. Okay, and now we can start plugging in some numbers, or actually maybe I should do some more rearranging. Yeah, let's do some more algebra with this. So the force of friction static is going to be, well, whatever that force of friction static is using inequalities, it's going to be less than or equal to some maximum static friction, which means it's going to be less than or equal to the coefficient of static friction maximum times the normal force. Okay, force applied minus force of gravity sine theta. Force of gravity sine theta, we got 40.52. Force applied was given as 57. So let's go ahead and calculate that, and let's switch to another color while we're at it. So force of friction static is going to be 57 minus 40.52 is going to be what? 16.48 if my math is correct. Let's check with the calculator. Yep, 16.48. I think that's what I said. 16.48 newtons. Okay. So that's our static friction needed. Let's go ahead and calculate our normal force over here. So that's going to be 15 times 9.8 for the force of gravity, and then times cosine of the incline angle, so times cosine of 16. And that's going to be 15 times 9.8 times cosine of 16 is 141.305. I'm going to round it to 141.31. So I'm going to say 141.31 newtons. Okay. Now that we have these two values, we can go ahead and substitute them into our inequality. So our force of friction static, I'll continue this up here. Our force of friction static, 16.48, is going to be less than or equal to our maximum coefficient of static friction times a normal force of 141.31. If we divide both sides by 141.31, 16.48 over 141.31 is 0.1166. I'm going to round it to 0.12. Or actually, I'll do 3 decimals, 0.117. So mu static maximum has to be greater than or equal to 0.117. A static friction coefficient of 0.117 or higher is needed. And that takes care of our second problem. Okay, where do we want to go from here then? Let me think. Do I want to pull some problems from the book, or should we just get started on the topic of pulleys? Let me look through the book and see if there are any good ones first. If not, we can just move on. I mean, there are plenty of good ones, but are they good for where we are right now? Or are they better saved for when we start venturing into the tougher problems? That one's a pulley problem, so we can't do it yet. This one might not be too bad. It gets us to do some geometry, and it's exactly the type of problem I warned about towards the end of last stream. So let's have a look at this one. It's got a diagram already drawn for us, and it shows us a block on an incline but this time the twist is there's a force applied in the traditional x direction. there is a force applied, like so. Force applied in that direction. Let's see what it says. It says a 2 kilogram block is held in equilibrium. We haven't really talked about that, but for now, it just means that it's held still. Well, still isn't even correct because an object can be in equilibrium while it's still moving. Just take it to mean that the net force is 0. That's basically the definition of it. Of course, there's more to it than that, but all in due time. We'll probably actually start off with equilibrium next time. Or, well, we'll do it next time. I don't know if we'll necessarily start off with it, but we'll see. Anyway, a 2 kilogram block is held in equilibrium. That just means net force on it is 0 in all directions on an incline of angle 60 degrees. So I drew the angle too small this time. And it's held by a horizontal force, F, applied in the direction shown in the figure if the coefficient of static friction between block and incline is 0.3. So mu static, and whenever they give you a static friction coefficient, they mean it's the maximum static friction coefficient, is equal to 0.3. If the coefficient of static friction between block and incline is mu static equals 0.3, determine, part A, the minimum value of the force applied, and part B, the normal force exerted by the incline on the block. So part A, minimum necessary force applied, and part B, determine the normal force. This implies that you can figure out what the applied force needs to be without having to figure out the normal force at all. I don't know if that's true, but we will see as we start doing the math. I have a feeling that we're going to have to calculate the normal force first in order to do stuff with friction. Okay, so let's go ahead and draw our diagram. Actually, I think I'm going to draw a second diagram with all the components. Right now, I'm just going to draw the raw component diagram. So, force of gravity straight down. Or did I say raw component? Just the raw forces, rather, not raw components. That doesn't even make sense. When I say raw, I mean undecomposed into components. And then we've got normal force pointing away from the incline like that. And then, let's see. So they said the minimum applied force necessary to hold it up. That would then imply that we're not applying that much force. It would imply that we are not applying that much force, just enough to keep this thing from falling, which actually tells me the direction of the static friction must be up the incline this time. Because if my applied force was greater than the minimum necessary, it could, well, let's put it this way. If the force applied was so big that in the absence of friction, the object would be sliding up, then it wouldn't be the minimum. Then it wouldn't be the minimum applied force. If we're trying to find the minimum necessary applied force, then there's not enough force to push this thing up the incline in the absence of friction. So that tells me that in the absence of friction, the minimum applied force would allow the object to actually slide down. So the force of static friction must be up the incline this time. You might want to pause and think about that one a little bit. But the reasoning is sound. Okay. Now I want to redraw this diagram with the components figured out. So we already know what the components of the gravitational force are going to be. We did that last time. We showed that, if you draw lines parallel to and perpendicular to the incline, then this angle over here ends up being equal to 60 degrees after doing some geometry, and that makes this perpendicular component the cosine component, and that leaves the other component as being the sine. What about for this force applied? Let's see if we can do something similar. So force applied goes along that direction, and if I were to break it into components, its components would have to be a component parallel to the incline and up the incline like that, and a component perpendicular to the incline and down like that. Those would be its components. So now I need to figure out an angle that I can use to break those components down. Let's redraw that. So the direction of the force applied is like that, and the incline is like this, and that angle is 60 degrees, and the components of the applied force are going to be like this and like this. So, well, since this is a horizontal line, it should be parallel to the ground, which is also horizontal. And if these two lines are parallel, then this line, this third line, the incline that's intersecting them, should intersect them such that this angle over here is also 60 degrees. So this angle over here should also be 60 degrees. Okay, and then since this component over here, this green component I drew, is parallel to the incline, then this horizontal line intersecting them intersects in such a way that this angle is equal to this one. So this is also 60 degrees. Then that tells me that the parallel component of the applied force is touching the 60 degrees, so it would be the cosine component, while this perpendicular component would be the sine component. So if I redraw my incline one more time, and redraw my forces as parallel and perpendicular components, then what I have is going to be this. Force of friction static, of course, is parallel and up. Normal force is perpendicular and up. Force of gravity cosine is perpendicular and down. Force of gravity cosine of 60 is perpendicular and down. Force applied sine of 60 is going to be perpendicular and down. So this is going to be force applied sine of 60. Down the incline, we've got force of gravity sine of 60. And up the incline, we've got force applied cosine of 60. Up the incline, we have, I guess, yeah, I'll draw it over here. Not drawn to scale. I'm drawing this one longer just to make room for it so that there's no confusion between this and this. force applied cosine 60. Okay, there we go. That will be our complete diagram, although the scaling of some of these vector components is definitely off. Hey, as long as the problem doesn't ask us to draw things for scale, we can get away with it. As long as we're not asked to draw them to scale, do whatever is convenient. Okay, what color do I want to use next? I guess we haven't really used orange all that much, so let's try and use it here. So, net force, let's see, net force, I guess I want to do, well, we have to figure out what the static friction force is. Yeah, there's no way around that, right? Unless, actually, no. We can do this without, yeah, we can do part A without part B. There is a way. So we can do, if I do net force in the parallel direction, net force parallel is equal to the mass. What was the mass again? It said it was a 2 kilogram block. I should have written that somewhere. I'll write it over here, 2 kilograms, so that I don't have to go back and look for it again, is equal to mass times acceleration parallel, which is going to be 0, equals forces up the incline minus forces down the incline, so that's going to be force applied cosine 60 minus force of gravity sine of 60. And I guess I should have written this one first, plus force of friction static. Let's see. So if it's the minimum necessary applied force, well, the minimum necessary applied force, is there... I guess the minimum necessary applied force would actually be 0, come to think of it, because if the static friction can go high enough to prevent this thing from sliding down without the need for any applied force, then I guess the minimum necessary applied force is actually 0 now that I'm thinking about it. Well, let's see what kind of friction coefficient would be needed for that. So, in the absence of an applied force, let's have a look. In the absence of force applied, force of friction static would just be equal to force of gravity sine 60. Would just be equal to force of gravity sine of, I'll just call it theta for now so that I don't have to write the 60 every time. And in that case, we could say coefficient of static friction times normal force is equal to force of gravity sine theta. Yeah, I'm not using the inequalities this time just because I'm kind of in a hurry to figure out if my line of reasoning is even correct here. And then the normal force, if we were to do net force perpendicular, if I were to do net force perpendicular equals mass times acceleration perpendicular, no perpendicular motion is expected, so I expect the acceleration to be 0. No perpendicular motion, and more importantly, as far as this is concerned, no change in perpendicular motion. Acceleration is about change in motion. It's not about the current motional state. But anyway, that would be normal force minus force of gravity cosine of 60 degrees, and also minus force applied sine 60. But in the absence of an applied force, this term would just be 0, and you'd be left with normal force minus force of gravity cosine 60 equals 0, so normal force would be equal to force of gravity cosine 60 in the absence of applied force. Mu static would be equal to force of gravity cosine 60, or theta rather, as I called it here. Force of gravity cosine theta. Mu force of gravity cosine theta equals force of gravity sine theta. And if I divide both sides by force of gravity cosine theta, then I get coefficient of static friction. Well, first off, force of gravity cancels out on both sides. And then I'm left with sine theta divided by cosine theta. That's equal to tangent of theta. So I would need a coefficient of friction of at least tangent of 60. If I plug in tangent of 60 into my calculator, let's see what we get. I get the square root of 3, which my calculator can rewrite as 1.73. So in the absence of force applied, coefficient of static friction would have to be 1.73, which is pretty high. Not impossible, but that is a pretty high static friction coefficient. It is not very likely that they intended for you to do this. Just call it a hunch, but I think the person who wrote this problem did not intend for you to assume that the minimum applied force was going to be 0. But if this was their intention, then the minimum necessary applied force is 0. That's just if the coefficient of... Wait a minute. What am I saying? We were given the coefficient of static friction. It's 0.3. So, yeah, we know definitively. I don't even have to guess. I forgot the information we were already given. So, yeah, you are going to need some applied force. But still, I think this was a worthwhile thought experiment. Just consider it like my bonus addendum to the question. You know I like to add extra stuff to some of these book problems. At least you should know by now if you've been watching all the previous streams. Okay, let's switch to pink now. So, yeah, to calculate the minimum necessary force applied, then I absolutely have to figure out what my static friction is going to be. And if I'm using only the bare minimum applied force, then the static friction is carrying as much of the load as possible. So my static friction force is equal to its maximum value in this case. It has to be maxed out. This has to be at its maximum. Okay, let's grab the pink and see what we can do. We actually have to calculate the normal force first. So net force perpendicular equals 0 equals normal force minus these two forces. So if I add those two forces to the other side, then I'm left with normal force equals force of gravity cosine theta plus force applied sine theta. And one of these is unknown, but that's okay. We can still work with it. Because now I can go back to this and go, let me see, what do I want to even solve for here? I guess I'm solving for the static friction, so I'm going to move these over to the other side of the equation. So I'm going to write force of static friction maximum equals, it would be adding force of gravity sine theta and subtracting force applied cosine theta. So force gravity sine theta plus, or minus force applied cosine theta. Okay, and I can substitute force of static friction maximum is just the coefficient of static friction maximum times this whole expression. So it's going to be mu static times, where did it go? There. Mu static times force of gravity cosine theta plus force applied sine theta equals force of gravity sine theta minus force applied cosine theta. I managed to squeeze it all in somehow, although it's probably not very readable. Okay, so I know everything in here except force applied. Force applied is my only unknown here. So what I am going to do is group the applied force terms together on one side. And it doesn't matter if I divide over the static friction coefficient because I would just have to distribute 1 over it on the other side. So we might as well just distribute it as is and not create unnecessary fractions. So yeah, I'm going to distribute that, but let's start that on another page because this is starting to look really messy. Okay, so let me move this up a little bit while I try to copy stuff over. So we have, I'm going to distribute the mu static. So we have mu static, force of gravity, cosine theta, plus mu static, or that should be mu static maximum, but we'll just call it mu static for now to save time. Times force applied sine theta equals force of gravity sine theta minus force applied cosine theta. Okay, if I add force applied cosine theta to both sides and I subtract this term over to the right, then what I'm going to get is, what color do I want to switch to? Let's use navy blue, which is just going to look black because of lighting effects. I mean, even with the natural lighting, I think it still looked pretty black anyway. So, what was I doing? Right, add force applied cosine theta over to the right side, so you get force applied cosine theta plus mu static force applied sine theta equals force of gravity sine theta stayed in its place. force of gravity sine theta stayed in its place, but we subtracted this. We subtracted mu static force of gravity cosine theta. Okay, I hope you remember some of the stuff that we learned way back in, what was it? Part 2 is when we looked at the math essentials. I hope you remember all the techniques we picked up from that, because this is going to give you flashbacks to it. We can factor out the force applied. And that leaves us with cosine theta plus mu static sine theta equals, and over here, even though I don't have to, I can factor out the force of gravity. So I'm going to go ahead and do that. Times sine theta minus mu static cosine theta. And to solve for force applied, I would just have to divide all this over to the right-hand side. So force applied is equal to force of gravity times sine theta minus mu cosine theta, and over cosine theta minus mu sine theta. How about that? Fractions that look like this have shown up on the free response questions for the AP exam in the past. And also you tend to see these kinds of fractions in the circular motion chapter, specifically when it comes to driving on a banked curve. And if you don't know what that is yet, don't worry. We will learn about it in due time. That's all in a future chapter. But yeah, knowing how to derive an expression like this, if you can master this skill, then you'll be in pretty good shape for any expression problem that they throw at you. Okay, now we can plug in all the numbers. I mean, we could have done it before, but then we wouldn't have this beautiful expression to gaze at. So force applied is going to be force of gravity mg. That's going to be, mass was 2 kilograms, so 2 times 9.8. And then times, I'm just going to use the fraction button here. So our angle was 60, so sine of 60 minus our coefficient was 0.3, and then that's cosine of 60 for the top. Wait, minus or plus? Oh, wait. Glad I caught that. One of these is a plus. This one has to be a plus. Okay. And then over, we have cosine of 60 minus plus, I did it again, plus 0.3 times sine of 60. Okay, putting all that together, I'm getting 18.47 newtons. Force applied must be at least 18.47 newtons. 18.47 is the number we get when we assume the friction is maxed out, so it has to be the minimum. It has to be the bare minimum applied force, and of course if we apply any more force, then that just means friction doesn't have to try as hard and the friction will be less than its maximum. That's our minimum applied force necessary. And would you look at that? It turned out we did solve it without having to calculate the normal force first. Kind of. We could have plugged in at any time and solved for the normal force before doing anything with friction. And if students were doing this normally and plugging in numbers as they go, that's what would have happened. You would have just calculated this normal force. Actually, no, you couldn't have, because the normal force depends on this applied force. Okay, so the order in which they asked us the questions this time is actually the order in which you solve them. I was expecting we might need to solve part B before part A, but I did say I wasn't sure about it, and I'm glad I said that. Otherwise, I would have ended up putting my foot in my mouth. Okay, so now, to calculate the normal force, this should be pretty easy now that we know the applied force. So it's force of gravity cosine theta plus force applied sine theta. Gravity cosine theta plus applied sine theta. Force of gravity cosine theta plus force applied sine theta. So that's going to be 2 times 9.8 cosine of 60 plus force applied we now know is 18.47 and sine of 60. I think this is the first time in this whole stream that I actually started going back to using parentheses around my input angles for my trig functions. I don't know why I wasn't doing that before. Maybe I was just subconsciously trying to save space, but I like to put parentheses around my arguments. It makes things, how do I say this? It makes things clearer? I don't know if that's the exact word, but close enough to what I'm trying to say. Okay, and I'm getting 25.795. 25.795. So that's going to be 25 point, I guess I'll round it to 0.8, 25.80 newtons. Okay, and now we are done with that one. Okay, it was a little bit tougher than what I was expecting it to be, but okay. Now let's talk about pulley problems. So, last time, I don't think I told you guys to do the... Let me switch screens. I don't think I told you guys to do the pulley problems over here, but I did say that you're welcome to look at them since I've got the solution videos explaining how to do everything. So if you took a peek at them, great. If you didn't, it's fine. Basically, with pulley problems, we're going to be doing pretty much the same thing we did last week with systems of objects. Pulley problems will typically involve multiple objects. It's not that much of a problem if it's just an object and then like a person pulling on the other end of the rope. That doesn't make for a very good pulley problem. But yeah, in this exercise I gave you a basic pulley on a horizontal table with no friction. Then I did another horizontal table with friction, and then I did an incline with no friction. And of course the next exercise, you put it all together. You've got systems of objects, pulleys, friction, and inclines all together. So that's where we're going. So let's justify the logic of working with pulleys. I'm going to start with I would assume most people did the first version of the problems, so I'm going to look at this second version here. It's basically the same problem set, but with different numbers in case you wanted more practice. So it says a block of mass 15 kilograms is placed on a smooth table. The block is connected to a rope that goes over a pulley. The other end of the rope is connected to a second block of mass 5 kilograms that hangs beside the table. What is the acceleration of this system, and what is the tension in the rope? So let's comment on this whole situation before we even attempt solving this. Let's talk about the assumptions that we make for pulley problems. Let me switch back to my document camera. Okay, so here are our assumptions about pulleys. Assumptions. Whoops, that's not how you spell assumption. Oh well. Let me try writing it over here actually so I have more space. Assumptions. About pulleys. If you have a pulley and it's got a rope running over it, I'll draw the rope in a different color. Let's say something like this. And let's say the pulley spins in this clockwise direction. In order for it to be able to spin, the actual truth is whatever force is pulling it this way, I guess I'll call this force Y, and I'll call this force X. Whatever force is pulling it this way, if this pulley is to spin clockwise, then there needs to be more force Y than force X. Force Y pulling it in the clockwise direction has to be greater than force X pulling it in the counterclockwise direction. And once we get to rotational dynamics, we will actually learn how to calculate exactly how big of a difference this needs to be according to how fast the pulley needs to spin. But we are not there yet. So, what we are going to assume about pulleys is two things, which aren't going to make much sense right now, but will make sense in the future. Once we get to rotational dynamics, we will see why these assumptions actually make it so that the way we do pulley problems before rotational dynamics is actually justified. So our assumptions are two assumptions. One, we assume pulleys are light. Assume the pulleys are light. Not heavy, in other words. And secondly, assume the pulleys experience no friction. Experience no friction. Once we learn about the concept of torque and the concept of moment of inertia, we will be able to go over these two assumptions and show in more detail why mathematically they allow us to get away with what we're going to be doing today. But for now, I'm just going to give you a little bit of intuition. I think most of you would agree without any proof. Most of you are inclined to believe, at least, that a lighter pulley will spin more easily, will require less force to spin. If you have two pulleys, a light one and a heavy one, and they both spin at the same speed or with the same acceleration, you would assume that the lighter one spins more easily, requires less force to keep up with the heavier one that's spinning at the same rate. Reasonable? Reasonable. And if there's no friction between the pulley and its axles, then that also means you don't require as much force. If you try to spin a pulley and you experience some sort of resistance, I wish I actually had some sort of wheel-like thing, but I don't. If you try to spin a pulley and it has some friction, then you're going to experience some resistance, which means you're going to have to push with more force to overcome that friction. So by assuming the pulleys experience no friction, there needs to be even less of a difference in force between the, I guess, clockwise and counterclockwise ends of the rope that are pulling on this pulley. So with these two assumptions, if the pulleys are light, they don't take a lot of force to spin. They don't take a lot of, I should say, net force to spin. I'm using the term net force loosely here because what it's actually supposed to be is torque, which we haven't covered yet. So not as much force difference is needed to make them spin, and with the friction, that also reduces the amount of force needed. So with those two assumptions, what we can say is that Fy and Fx are approximately equal. Fy is approximately equal to Fx. So if Fx was, I don't know, something like 12 newtons, Fy would be 12.00001 newtons in order for this pulley to be able to spin. That's kind of what we're arguing here. So Fx and Fy then are pretty much equal. As far as our math is concerned, the difference between them is just, it might as well just be a rounding error. So yeah, that's what we're going to assume about pulleys for now. That if a rope goes over a pulley, even though it's technically cut up into different sections by the pulley, and each section is supposed to be independent of the other and can have different forces, we're going to assume for the time being that these forces, as long as it's the same rope, we're going to assume that the magnitude of the force is the same on both sides of any given pulley. That's going to be our assumption for now. Good? Good. Now then, let's go ahead and look at our problem and see what we can do with it. So it says a block of mass 15 kilograms is placed on a smooth table. The block is connected to a rope. Actually, you know what? I'm going to pull a problem from the book. Let's pull a problem from the book. Let's not use this color yet. How about the light blue? Okay, so the book problem says it's got a table over here and a pulley on the corner of the table. And it says an object with mass 5 kilograms rests on a frictionless horizontal table. So 5 kilogram object right here, 5 kilograms. And is connected to a cable that passes over a pulley and is then fastened to a hanging object with mass 10 kilograms. So there's going to be a cable, rope, whatever you want to call it, it's all the same. And hanging off to the side is a 10 kilogram object like this. And it's not touching the table. I don't know if that gap is very visible at the size I've drawn it at, but there is a gap there. There's no physical contact between the 10 kilogram object and the table. It says find the acceleration of each object and the tension in the cable. Find the acceleration of each object and find the tension in the cable. So going back to this a little bit. So when a rope is divided into sections like this, if a rope isn't completely straight, if a rope gets bent at an angle or whatever, then every straight section is going to have its own tension throughout that whole section. So in this case, this rope was divided into two sections, a horizontal section and a vertical section. Whatever the tension is at one point in the horizontal section, the tension is the same at all points in that horizontal section, and the tension will only change once you bend it. For pulleys and our assumptions about pulleys, this bending of the rope around the pulley isn't going to make a significant difference, as we've just argued, but we will see problems where, for example, we have a problem in my book about like a bird feeder hanging from a bunch of ropes like this, and like this is all one rope over here. This V shape is all one rope, but it got bent into two ropes essentially, so you're going to have a different tension in this section compared to this one. So just remember that for when we do those sorts of problems in the future. Anyway, back to the problem at hand. So all it said was find the acceleration, the table is frictionless, we can go ahead and draw diagrams and get going. So let's do, I think I can just draw the diagrams on here. Yeah, I think there's enough space. So for the 5 kilogram object, we've got normal force upward and force of gravity downward. I guess technically I can call this force of gravity 1 since it's object 1, just to keep it distinct. And then there should be a force of tension to the right. And that should be it. No friction to consider. For the 10 kilogram object, we've got a force of tension upward, which is approximately equal to this force of tension. That's why I did not give it a different name, right? We are assuming a light and frictionless pulley here. And other than that, the remaining force for the 10 kilogram object is just the force of gravity. I'll call it force of gravity 2. And that's what we have to work with. So when working with pulleys, you have to make an assumption about the direction that the pulley will move, and that will help you define where your positive direction is. And if your assumption is wrong, you have to go back and redraw your diagrams, especially if, well, you don't always have to redraw your diagrams, only when you have forces like friction that depend on the direction in which the system moves. Otherwise, if you guess incorrectly, all that you have to do is slap a negative sign onto your answer in the end. Just whatever answer you get, change it from negative to positive or positive to negative, and you'll be done. And it's a quick fix, but if friction is involved, then you have to go back and redraw diagrams. So it's a good idea to learn how to just kind of, you'll pick this up subconsciously, I imagine, just through doing a bunch of problems. You'll start to gain an intuition for which direction the pulley is going to spin. So in this case, I think we can all agree there's nothing pulling the 5 kilogram block to the left, so the only direction that this system could possibly move is with the pulley spinning clockwise. So I'm going to say clockwise spin for my pulley is the positive direction, which means we're going to interpret, the way that we're going to interpret this is that down is positive for this 10 kilogram block, while right is positive for this 5 kilogram block. That's what this pulley spinning clockwise means as far as we're concerned. The positive direction is the direction we assume everything moves in. So We assume the 5 kilogram moves right, so we use right as our positive direction. We assume that the 10 kilogram object moves down, so we're going to use down as positive for it. And as long as you do that, then your equations will work out really nicely. Otherwise, if you want to do the same thing we've been doing and use up is always positive and down is always negative and right is always positive and left is always negative, well, then you're going to have a bunch of different accelerations that you need to account for. You're going to, like, if we did it over here and we said down is still negative for the 10 kilogram object, then when we calculate the acceleration y for the 10 kilogram and the acceleration x for the 5 kilogram, we're going to have to make sure that we say that the acceleration in x is equal to the negative of the acceleration in y to show that they're equal in magnitude, despite one being negative. And that's just too much of a headache. I'm sure you guys just got a headache listening to me trying to explain that. So let's avoid the headache and make smart choices for where we want our positive directions to be. Okay. So object 1, normal force and force of gravity on object 1 aren't really going to do anything for us here. It would be a useful relationship if we had friction, then we would need to calculate what the normal force is, but there's no acceleration vertical here. I guess we'll write the equation anyway. Net force for object 1 in the y direction is going to be 5 times 0 equals normal force minus m1g, so 5 times 9.8. Tells us that the normal force is 49, which isn't really useful information for us here. Net force x is the more relevant one for us. Net force object 1, x. That's not a very good y. It looks kind of like a g. That's a little bit better. Anyway, net force 1, x, is going to be 5 times the acceleration in x, or we can also just call it the acceleration of the system, equals, only force in the x direction is the tension force. Okay, and for the 10 kilogram object, there is no net force x, there's only a net force y, so net force object 2 in the y direction equals 10 kilograms times, I'm going to call it acceleration of the system again, equals forces down minus up this time. So force of gravity, I can't talk today. Force of gravity 2, which is 10 kilograms times 9.8, minus forces up minus the force of tension. So essentially what I'm saying with these two statements here, by subbing in acceleration of the system, what I'm essentially saying is the acceleration of the system is equal to, or opposite direction, think about it in the opposite direction. The acceleration of object 1 in the x direction is equal to the acceleration of the system, and then the acceleration the acceleration of object 2 in the y direction, or rather the negative of it, if you assume down to be the negative direction in y, is also equal to the acceleration of the system. That's how you want to think about it. And then this would make sense, because if you substitute a system with negative acceleration to y, then the down minus up starts to make sense. It starts to be consistent with what we've been doing up until this point. So just more food for thought for those of you who were still worried about that little detail and felt that I was being a bit too hand-wavy with it. Anyway, 5 acceleration of the system equals force of tension, 10 acceleration of the system equals 98 minus force of tension. We saw this last time. This is just what typically happens when you're dealing with a system of objects. Add these equations together, and what do we get? Color. What color have we not used in a while? I guess purple. If I add these equations together, I get 5 plus 10 is 15. Acceleration of the system equals force of tension, and minus force of tension disappears, and we're left with 10 times 9.8, or 98 newtons. Divide by 15, and let's see, what do we get? 6 and 8/15. Okay, calculator. 98 divided by 15 is about 6.53. The acceleration of the system is 6.53 meters per second squared, which just means 6.53 to the right for the 5 kilogram object and 6.53 down for the 10 kilogram object. So that is, was that the only question it asked? Let me see. Find the acceleration of each object and the tension in the cable. Well, now that we know the acceleration, just plug it into, I would plug it in over here, and that's it. Multiply by 5. 6.53 times 5 is 32.65. So we get a force of tension equals 5 acceleration of the system, and I'm getting about 32.65, or I guess 66, depending on how you end up rounding. Actually, wait, would it be? Let me see, if I took the original number and multiplied by 5, yeah, if you took the original number and multiplied by 5, you'd get 32.67 actually. So that's why the sig fig rules exist. But again, we're going to worry about sig fig rules when and if we're working for NASA, or if you're taking a PCAM. And I forgot the units. Newtons. 32.65 newtons. Okay, there we go. So let's go back and look at the net force on the system. Let's go back and look at the equation for net force on the system. So I warned about this last time, although you didn't know that I was talking about this. Here's where things get weird if you try to draw a diagram for the system. So this is just warning, not something you actually need to know. Don't worry about this too much. Worry about this after you've mastered the basics and how to do it the normal, traditional way. But if I were to draw an object that represents both of these objects together, then I have a bit of a conundrum, because there are two possible diagrams for this. One way I could do this is I could combine the 5 and 10 kilogram objects into, this is a 15 kilogram object that has a net force of 98. And I could draw it like this. So a force with a magnitude of 98 newtons acting on it to the right, or perhaps we should draw this. Where the system has a net force down of 98 newtons. Which one is the truth? Well, neither of them is the absolute truth. Neither of them are the absolute truth. But one way you could interpret this, the two ways you could interpret this are either that you have a 15 kilogram object that for some mysterious reason is being pulled down by 2/3 of its actual weight, or you could also think of it as the 10 kilogram object, and this is probably the interpretation that most people will take because it's a little bit more intuitive. It's a little bit more acceptable to most people's minds. Most people like to think of it like this. The hanging 10 kilogram block, its force of gravity is transferred through the rope to the 5 kilogram object. So it's as if the 5 kilogram object is being dragged sideways with a force of 10g. And yeah, this is what most people are more comfortable with, but it's not the truth. Sideways gravity doesn't make sense, right? Gravity is supposed to be straight down, so what's going on? The way people like to interpret it is that the force of gravity curves sideways because it's kind of quote-unquote transmitted through the ropes. I say quote-unquote because that's not the actual truth, as I would hope we can plainly see just from what our original diagram looked like. But if that idea of sideways gravity is appealing to your mind, if you see an opportunity in trying to learn, trying to understand this sort of shortcut to save yourself time, then by all means go for it. But again, heed my warning from last time and earlier today about shortcuts. Make sure you understand your shortcuts before you use them. And even then, especially on an exam, don't take chances with it. Do things the traditional way and use your shortcuts just as a quick way to check as you solve the problem. Use it as a quick way to check that you're heading in the right direction. If your shortcut can quickly tell you what you should be getting, and then you go and do things the slow and steady way, it'll help you catch problems because you'll know in advance what to expect, and you'll notice more easily if something is off. So those are my 2 recommendations for shortcuts. Don't use them until you understand them, and if you can't prove them, then you probably don't understand them, so make sure to prove them, and after the proof, make sure you understand the proof and understand the conditions and all that. And secondly, still, try to only use them as additional avenues of checking for errors. Unless you're doing the physics SAT, where for some ridiculous reason they expect you to solve each problem in, I forget what the exact number was. Was it like 48 seconds per problem and with no formula sheet? Not that you would even have time to look at a formula sheet, given what little time they give you per problem. Yeah, for that shortcut equations are probably going to be important. But for AP Physics, you shouldn't have to resort to that. Just focus on learning the concepts for now, and maybe if you go further in your career with physics or end up teaching physics to someone else yourself, maybe then, after you're done with the course, go back and see if you can master these shortcuts. But for now, your priority is just make sure you know how to do things the normal way and you'll be fine. Okay, so I guess we can do... Do I want to do this one? I mean, it's quick and simple, but I don't know if it's the most relevant thing I can do. Okay, let's do, actually, let's do one with an incline, or maybe two. Hold on, do I have one with an incline that has friction on it? Yes, I do. Okay, let's do this one, and then we will wrap up with that. I'm probably not even going to be able to fit it over here, but we will try. It says, find the acceleration reached by each of the two objects shown in the figure if the coefficient of kinetic friction between the 7 kilogram object and the plane is 0.25. I will read it again, but let me copy over what they have. So they have this, an incline of angle 37 degrees, which I clearly did not draw to scale. And there's a 7 kilogram object. And a pulley. And a 12 kilogram object. And they're connected by some sort of rope, or I guess they called it they didn't call it anything, so we can assume whatever. Rope, cable, chain. Probably not something as flimsy as a piece of yarn or dental floss if it's going to be carrying a 12 kilogram object on one side. I would imagine it's something somewhat sturdy, like a rope or cable or wire. Okay, so it said, find the acceleration reached by each of the two objects shown in the figure if the coefficient of kinetic friction between the 7 kilogram object and the plane is 0.25. So this incline does have friction on it, and the coefficient of kinetic friction is 0.25. And since they only gave us a kinetic friction coefficient, that implies that the system is definitely going to move and that the static friction coefficient is not high enough to prevent it. Otherwise, they would have given us that number and we'd have to check first. Okay, so nothing too bad here. We can just draw our force diagrams for the two objects. I'm going to draw one for the 7 kilograms here. So here's my 7 kilogram object, and the forces acting on it are going to be, no, let's not use that color. We've used it for too long today. Let's do purple. We've got force of gravity sine theta this way. So 7g sine of 37. And force of tension. What else? We have a normal force. And we have a force of gravity cosine theta. Force of gravity, so I guess 7g cosine of 37. And we're going to have a force of kinetic friction. So what would be your guess? Will this system move with the 7 kilogram object going down the incline and the 12 kilograms being pulled up? Or with the 12 kilograms going down and pulling the 7 kilograms up the incline? Intuition would suggest the heavier block does the pulling, so I'm going to guess that this pulley spins in a clockwise direction, so that's going to be my positive direction there. So if I'm assuming that this 7 kilogram object goes up the incline, then my kinetic friction would have to be opposite to the direction of motion, down the incline. So force, friction, kinetic would have to be like this. This is based on an assumption. I am assuming that the system will move like this. What if my assumption turns out to be wrong? Well, then I have to go back and redraw this diagram and correct the direction of my kinetic friction force. That's really all you have to do to fix this. Okay, so that's the 7 kilogram object diagrammed. Now for the 12 kilogram object. For the 12 kilograms, actually I'll just diagram it here. It's pretty simple. It's just force of gravity down here, so 12G, and then force of tension upward. And if we assume the pulley is light and frictionless, then this force of tension must be equal to this force of tension, so no need to call them tension 1 and tension 2. We'll just say that they're approximately equal. Okay, now we can write down our net force equations for each object. For the 7 kilogram object, the relevant net force equation is going to be the one parallel to the incline. But to calculate friction, we need to know normal force. So normal force, if we look at the perpendicular direction to the incline, the only thing that interacts with the normal force is going to be the cosine component of the gravity. So normal force minus 7g cosine 37 is going to be equal to 0, since I expect no acceleration along this perpendicular direction. Might as well draw my coordinate system there. So yeah, normal force is just going to be equal to 7g cosine 37. We've done this enough times by this point that I don't think you need me to show you the math anymore. So now that we know that, we can write in for our force of friction kinetic. Force of friction kinetic equals coefficient of kinetic friction times normal force equals 0.25 was our coefficient, as we were told in the problem, times our normal force is 7g cosine 37. Okay, then we can plug those numbers in and figure out what they amount to, and we'll do that in a second here. Net force parallel for the 7 kilogram object. Let's switch colors here. Yeah, we'll do light blue. So we get, if my pulley is assumed to spin in the clockwise direction, then my positive direction is up the incline. So force of tension is positive, and these two forces are going to be negative. Those two negative, that one positive. So net force on, I guess I'll call the 7 kilogram object 1, and I'll draw it with Saros so as not to confuse it with the double lines for the parallel direction, is equal to, the mass is 7 times the acceleration parallel is equal to the acceleration of the system, equals force tension minus 7g sine 37 and also minus the force of kinetic friction, which is 0.25 times 7g cosine of 37. All right, and then net force, I guess y, for the 12 kilogram object, with down being the positive direction, since that would be the direction it moves if the pulley spins clockwise. Net force on object 2 in the y direction is going to be 12 kilograms times the acceleration of the system equals, down is positive, so 12g minus force of tension. Okay. If I add these equations to each other, then the force of tension gets eliminated. We've seen this happen how many times now between last stream and today? Actually, how many times did it happen today? I think only once, right? Over here. Did we do anything else today that... No, yeah, it only happened one time today, but happened plenty of times last week, so this shouldn't look foreign to you by this point. Yeah, force of tension and minus force of tension cancel out, and we're left with 12g minus 7g sine 37 and minus 0.25 times 7g cosine of 37. I'm going to go ahead and plug in all those numbers on my calculator. So 12g, 12 times 9.8. Actually, I'll leave the g for the very end since they all have g in them. So I'm going to do 12 minus 7 sine of 37 degrees and minus 0.25 times 7 times cosine of 37 degrees. Did I do that right? 12 minus 7 sine minus 0.25 times 7 cosine. Yep. And that's 6.38968. And then all that times g, so times 9.8, is 62.6188. I'm going to round to 62.62. I'm going to round to 62.62. So 7 plus 12, 19, acceleration of the system is equal to 62.62 newtons. And if I divide by 19, I get an acceleration of 62.62 divided by 19 is 3.2957. I'm going to round that to 3.30. So the acceleration of the system, is that still visible on the screen? Yes, it is equal to 3.30 meters per second squared, give or take. So that was the first thing they asked, and let me guess, did they also want the tension? No, all it says is find the acceleration. Okay, but if they did ask us to find the tension, then actually I think I would rather use this second equation since it has fewer terms in it. Even if it means having to deal with that negative sign. Dealing with the negative sign is probably less hassle than dealing with all that. Okay. Anything else I want to say about this problem before we start talking homework and preparation for next time? Anything of note about this problem? Oh, well, since the acceleration of the system came out positive, this confirms that my guess for the spin direction of the pulley is correct. If you guess the direction that the pulley rotates and you set that to your positive direction, and then you determine the positive directions of each of your individual objects based off of that, then if your guess is correct, you should get a positive acceleration for the system. If you get a negative, then it might just be the exact negative of the number you want, or it might mean that you have to start over and correct your diagrams. I mean, you don't have to completely start over. Most of the time, the one thing that's going to change is the direction of the friction on your diagram, which will change the sign of the friction in your equations. And those are actually relatively quick modifications, even if it is annoying that you still have to go back even to correct a few small things. But you'll understand, you'll get a feel for it. With enough practice, you'll start to develop a sense for when the pulley will spin one way or the other. It's not always necessarily the case that it will spin in the direction of the heavier side. So counter argument to this, and actually let's leave you with this as a homework problem. If you have two masses where M1 is heavier than M2, so M2 is hanging off to the side, M1 is on the incline, and M1 is heavier than M2. M1 greater than M2. And the angle is theta. Set it to be whatever you want it to be, or just keep it unknown. Actually, you should be able to find a solution where you still keep theta as an unknown. Tell me, under what conditions will the pulley spin clockwise versus counterclockwise when M1 is the heavier block? Just because it's heavier doesn't mean that it's always going to pull down the incline, causing M2 to go up. You have to remember that the incline itself supports at least part of the weight of M1. So from the perspective of M2, M1 feels lighter than it actually is, if that makes any sense. So play around with this. Again, the question is, if M1 is greater than M2, then under what conditions will the system move such that the pulley rotates clockwise versus counterclockwise? That is what I want you to think about between now and next time. And other than that, let's see what we should do for homework. What would I suggest? So if you haven't done these pulley problems, then go ahead and do them. Same thing for these inclined plane problems. If you haven't done them, then I would recommend doing them. This was the part of my homework series where I started creating multiple copies. Let me see, was it here? No, the pulley problems. This was where I started creating two different forms, a form A and a form B for my questions. Just basically the same problems, but two sets with different numbers. So yeah, from this point onward, if you're looking at my homework PDFs, which there aren't that many of them left, I kind of stopped doing them once I got into energy. But if you look between those two, and again, they're just linked in the course plan, which itself is linked in the description, it would be under over here, pulleys and pulleys with inclined planes. If you get stuck, you can click here for the solution videos. And yeah, as far as this list is concerned, it looks like we're done with force, but oh boy, are we not done with force. You can, at least at this point, you should be able to do all the conceptual questions and problems and exercises, except maybe if they have some for the spring force, which I haven't really talked about. We're gonna save talk of spring force for the next chapter, because springs, we see them come up more often once we have some energy problems to work with. So that's when I will discuss the spring force in more depth. Although I guess I can give you a quick here's the formula for it. So here's a spring, and the amount of force it exerts depends on how much I stretch it. Actually, I did show you guys a couple weeks ago my spring scale. Let me actually show that, because that's even better at illustrating the idea. Where did I put you? There you are. So here's one of my spring scales, and over here you can see that it's labeled in newtons, and then you've got the little white thing indicating where the spring is currently at. And now that I'm pulling it, you can actually see the spring inside there. But yeah, basically, if I pull it, let's call this a centimeter, then that's 0.25 newtons of force. If I pull it 2 centimeters, that's double the amount of force. If the spring is what we call an ideal spring, then the amount of force that is exerted by the spring, trying to counter the force of my hand pulling on it, is just equal to some constant times the length to which it is pulled or pushed. It also works in the opposite direction, where if I push an ideal spring by, what did we call this, 1 centimeter? If I was able to push it 1 centimeter, that would also create a force of 0.25 newtons. Assuming that this is actually 1 centimeter, which looks like it's a little bit less than that, but just for the sake of example. So the formula for the spring force, if you want to look at it early, this is Hooke's law, named after, what was his first name? Robert Hooke, I think it was. Hooke's law is spring force is equal to negative kx, where x and the spring force are vectors. The negative sign just indicates that the direction of the spring force is opposite to the direction of the push or stretch, opposite to the direction of the stretching or the compression. If you pull on a spring, then it will exert a force in the opposite direction and pull back. If you push on it, it will push back. So that's what the negative sign means. Normally, we would just put an absolute value on this and focus on the magnitude of the spring force and indicate the direction in our diagrams instead of using a negative symbol on it. And the K, that is called the spring constant. Basically, it's the stiffness of the spring. This spring does not stretch very easily. If I want to stretch it by 2 centimeters, it takes more effort. It takes more force than stretching this one by 2 centimeters. I think you can tell just by looking, even though you can't feel it. I think you can tell just by looking at this spring that it's a little bit looser and easier to stretch than this one. So that means that this spring, the looser one, is going to have a lower K value. It's going to have a lower spring constant, whereas this one has a higher spring constant. And then the springs in your car, for example, if you have a car, probably your parents' car if you're not old enough to drive yet, the springs in there for the shock absorbers, right? Those use springs. Those springs are really, really tough and have an extremely high K value. And then you have this thing. This thing is not even really a spring, it's a slinky. This thing stretches really easily. I don't even have to put in effort. All I have to do is just hold it down and it stretches under its own weight. That's how easily this one stretches. So this one has the lowest K out of all 3 of these. If I were to treat it like a spring, it's not really a spring because There are things that look like springs that don't actually behave like, well, they may be springs, but they might not be ideal springs. And the force required to stretch or compress them is not directly proportional. It doesn't have a linear relationship with the distance to which it's compressed or stretched. If the relationship is non-linear, if you have something where the force is something weird like something like negative k1x squared plus k2x, anything other than this linear relationship, then it's not an ideal spring. It doesn't obey Hooke's law. And for AP Physics 1, you're not really going to encounter this. In AP Physics C Mechanics, you might be given descriptions of things that behave in this way, and they might expect you to do a bit of calculus with them, but we'll cross that bridge when we get to it. Again, for those who didn't watch my explanation of the course structure in the first stream of this series, I'm doing the calculus-based stuff after we are done with doing everything algebra-based. So if you came for Physics C and you want calculus-based stuff, I don't like to teach the calculus along with the physics. I like to learn the physics first and then add in the calculus, because I feel like teaching the physics along with the calculus just makes it so that the students get way too fixated on trying to use calculus on everything, and doing everything algebra-based before that point really helps you gain a sense for how far algebra can get you, and it'll help you kind of recognize when you do and don't need calculus. But that's enough rambling from me. Let me get back to homework. So this problem over here, I'll state it again. If M1 is greater than M2, under what conditions will the pulley spin clockwise versus counterclockwise if M1 is greater than M2? What are the conditions? And I'll leave it up to you to try and interpret what that would even mean mathematically. Then for other practice, I already mentioned, do the inclined plane and pulley exercises if you haven't done so already, and you should be able to do all of the problems and exercises now. You might get some that mention air resistance, and in those cases the problem itself will give you a formula for air resistance. Just use whatever the problem gives you and see what you can learn about it. And actually, well, we'll do one. I'll have to remember to do one among the problems that we do in the coming weeks, and there should be one or two in there already, so even if I don't specifically remember, I'm going to run into it going down the list anyway. So if somehow I get to the end and I do forget, then by all means, if you're there during the stream, just shout at me in chat and remind me to do it. If I end a stream talking about how the next stream is going to be energy and you know I haven't done an air resistance problem yet, then just make sure to yell at me and we'll get that dealt with. So I'm thinking, how many weeks? Actually, I don't even want to make any assumptions. I'm just gonna, for the next couple weeks, we're gonna look at problems that I think are, what's the word? We're going to look at problems that are very informative, problems that will teach you some of the intricacies of force problems that will, some of which will throw you for a loop. Some will be simple, straightforward, and that's okay because there are still some simple concepts that we want to expose ourselves to when it comes to force, but there are also going to be some more complicated stuff, and there's definitely going to be some problems where kinematics comes into play. I haven't forgotten about that so far. Any force problem I've done with kinematics, the kinematics has been rather simple, and usually it's just calculate the acceleration. Okay, now calculate how far you traveled in 5 seconds given this acceleration and starting from rest. Well, we're going to do things that are a bit more complicated than that, so that's coming. Next week, equilibrium and other, I'm going to say like two-dimensional force stuff. I'll look at the problem list ahead of time and figure out how I want to title the next stream, but yeah, I think that is it for now. I feel like there's something else. I already said no traditional office hours this week either, unfortunately. Maybe next time. We will see. There is one sort of physics problem that I want to do for traditional office hours. Otherwise, I kind of want to continue with calculus stuff, but I need to think about what kind of calculus stuff I want to do next. So I have some figuring out to do. I had a list of specific problems I wanted to look at, but it's been a few weeks since I came up with that list, and I don't quite remember everything that was on that list, but that's a problem for me to figure out. That's enough of me rambling. Take care. Hope you learned something today. Class dismissed.